And the experiment that was done so far includes 3 stations, but there are more that one can use, and in principle, one can use also the SPT. That will be very helpful, and other forthcoming millimeter observatories in realizing such an array. Another frontier that will probably mature in the coming years is the discovery of Earth-like planets, possibly in the habitable zone if they exist. And that would be very exciting because it will give us prospects for life elsewhere in other systems like the solar system. And of course, the Kepler satellite is the best instrument for that purpose. So tune in to the next TED lecture given by Dimitar Saslov. Forget about the previous one.
Just replay it.
No, I'm not sure that, as I said at the beginning, prophecy is not really something they should anticipate. Of course, the other way that the sky was not observed at is in the time domain. And there are new observatories that are being constructed, that will give us much more information than was obtained in the past. So this is, again, a new frontier, observing the sky in the time domain. We have pan-stars and the TPF, and we have plans for the LSST. And of course, W first will also be used for that purpose. So the goal would be to actually map new transients on the sky, new types of explosions or variable sources that we haven't observed as of yet. And since we haven't really explored this time domain in great detail, this would be a new frontier. Of course, cosmology will remain a frontier. And the nice thing about cosmology is that if you go back in time early enough, the universe was very simple. 20, 30 years ago, people thought that the reason cosmology is simple is because we don't have much data about the universe at early times. Especially people that didn't work in cosmology argued that it's simple because of the lack of data. But now we have the data. And we know that the initial conditions of the universe were very simple. They can be summarized on a single sheet of paper. And we have that sheet of paper. This is the sheet of paper. And you can summarize statistically the nature of the initial perturbations that the universe had. It was uniform by and large. It had perturbation, and we know the general properties. We have error bars that can be improved in the forthcoming years. And we have a standard model of cosmology. You might wonder how come the present-day universe is so complex that there are thousands of books in libraries that cannot summarize even a small portion of the universe, like the US politics or economy. Or how come this complexity arose from such simple initial conditions? And the answer is gravity. So all the complexity you see nowadays was reflected in the simple initial conditions that the universe had. There was nothing else. Just gravity made galaxies, inside of which stars were made like the sun, next to which there was some debris left over that made a planet like the Earth, on the surface of which there was liquid water, some chemistry, and we came along. That's it. In terms of cosmology, we have an image of the universe when it was 400,000 years old. And we have images of galaxies and large-scale structure more than 1 billion years after the Big Bang. We're still missing some pages in this photo album of the universe. And that's one of the goals of the next decade, to fill up this photo album of the universe. And it's not just a matter of filling it up. Obviously, the picture of an adult is not a scaled-up version of a fetus. There is something in between, so we want to understand how the galaxies we see around us today came into existence. We can also test gravity, how density perturbations grew, and on small scales that became nonlinear by the present time. If we go back in time, these scales were still in the linear regime, so we can probe the initial conditions more directly. And the SDSS-3 in particular, that Daniel Eisenstein is leading, might actually provide us with a probe of a major fraction of the volume, the observable volume of the universe. 21 centimeter cosmology might also probe a substantial fraction of the observable volume. And by seeing the perturbations grow in time, we can actually test our understanding of either the dark matter or gravity. Of course, there will be also the successor to the Hubble Space Telescope, the James Webb Space Telescope, that will search for the first galaxies. Hopefully will be launched within 4 years. And the three big telescopes that are being designed right now, the Giant Magellan Telescope here, the 30-meter telescope, and the European Extremely Large Telescope, which is the biggest among the three, 42 meters in diameter. Another approach, as I mentioned already, to probe the very early epochs that we haven't probed yet, or to map the distribution of matter through the universe, would be to observe the 21 centimeter line of hydrogen. And there we should be able to see, hundreds of millions of years after the Big Bang, we should be able to see cavities in the distribution of hydrogen due to the ionizing photons from the first stars, the first galaxies. And these cavities will grow in size and eventually overlap. We know that they overlap by a redshift of 6. And the experiments to do this, to perform this measurement are listed here. We are partners in the MWA. There is also the LOFAR team in Europe and some other experiments. And I should mention here that even though most of the work in this field is using interferometers, it's quite remarkable that there are a few people that go out of this mainstream. And one of them is shown here. And this is an experiment led by Alan Rogers and Judd Bauman that are constructing a single dipole to image the 21 centimeter radiation across the sky. So in other words, not worry about the pattern on the sky, but integrate across the sky and then look at it as a function of frequency. And if the universe was ionized at a particular redshift, you would expect a step, a spectral step in the background radiation associated with the 21 centimeter line. And I regard this experiment as very promising. In fact, there is a Nature paper in the pipeline right now that reports about the first constraints on reionization from this experiment. So these are examples for frontiers that I see for the coming decades. And an interesting question for young people is, what is the optimal strategy for selecting a research topic? And the analogy I make is with investments, monetary investments. And I divide those into three categories based on the level of risk. So there are bonds. These are topics that are pretty secure, that you can invest research time in and get predictable results, predictable outcome, although the benefits are modest. Precision cosmology belongs to this. Just refining our knowledge, reducing the error bars in the cosmological parameters. Refining our constraints on the lambda CDM model. Exploring star formation. We know that there is no new physics there. It's just a matter of understanding the details. Black hole feedback is the same. Constraining inflation is also becoming a bond these days. Stocks. These are more risky projects. For example, imagining that we don't have a cosmological constant, that the equation of state of the dark energy is evolving with time, with cosmic time. Searching for the dark matter, either in the Large Hadron Collider or in direct detection experiments from the Milky Way halo. Searching for annihilation or decay products of the dark matter. It's a risky proposition because maybe the dark matter is not what we expect. It's like looking for an extraterrestrial civilization, assuming that they look just like us. But we don't know what they look like. Then there are the very risky projects. And in fact, I should comment that I got some of the emails that I got were from people that suggested that some of these topics, for example, anthropic reasoning, might be like investing with Madoff. They said, I'm not really venture capital. They're like investing with Madoff, but I leave that distinction aside. And for example, if we imagine a modification of gravity, either in the form of modified Newtonian dynamics or f of r or other forms on the scale of the horizon of the universe, that's a venture capital investment. Okay, we don't know if it will bear any fruits, but if it does, it will be a major revision of our view of the universe. Anthropic reasoning is another one. And in fact, it's very popular among string theorists, for example, these days. And that may tell you something about string theory more than anything else. There are people that propose that there is no Big Bang. There was no Big Bang. The universe is cyclic. There was no inflation. The perturbations were produced by other means. And there are papers every now and then about variable constants of nature. In fact, the latest fad is that the fine structure constant is not changing in time, but it actually changes in space. So,
Avi, how about exoplanets? How would you put that on there?
there is a good reason why I didn't put it on this. I have no way of deciding whether intelligent life is a likely proposition or unlikely proposition. So I would put a flat prior on that. I would put it in all three categories. So if you are thinking about SETI, for example.
Before that, long before anything about intelligent life, just exoplanet characterization.
Just measuring the existence of exoplanets, I think, is a bond. I mean, we know that they exist. There are a few, more than almost 300 now. So it's very likely that 600 by now. It's very likely that there are systems that are similar to ours elsewhere. Okay? The question is whether life developed. And that, I think, is the more interesting question. And on that, primitive life, I think, is likely to have developed, but it would be nice to find out evidence for that. And intelligent life is the question mark that I mentioned at the beginning. So an important question in this context is when to invest in a bond, stock, or venture capital. And let me give you an example. Suppose we consider whether to write papers on dark matter or on modified gravity. Omega B or not omega B. That's so the answer for that is relatively simple. When the upper limit on the cross-section for interactions with nucleons is up here, then you might think that MOND is a crackpot idea, that modified gravity does not make any sense. When the upper limit is down here, so that most reasonable theories are ruled out, you might think that it's an attractive alternative. So it all depends on the timing. And timing is a matter of choice. It's a matter of personal preference. And you can decide when to enter that speculation. But what I noticed recently is that there is an alarming trend. When I speak to young postdocs at the ITC, for example, I find very surprisingly that they are much more conservative than I am. And that's alarming to me. Because 2 decades ago, when I was a postdoc, we were speculating on many different things. And I was wondering, how come, unlike decades ago, young researchers are investing in bonds mostly? Why is that? There must be a sociological reason for that. And I think the answer comes from job security. There are many more people competing for jobs these days. Also, there is peer pressure because we have a standard model in cosmology that didn't exist more than a decade ago. And since we have a standard model, there is psychological pressure on people to subscribe to that. And moreover, there are large research groups. SDSS-3 is an example. And they, because of the funding agencies, have predictable research agendas and very tight schedules. And when you belong to a big group, you develop a herd mentality. You have to subscribe to the agenda of the group. And my definition of a large group is that the list of authors is bigger than the abstract of the paper that they write. That's a simple definition.